Welcome to this presentation. Today we are going to discuss again the questions and the answer regarding thermochemistry. If you remember last time we ended on question 40, today we are starting question 41. Question 41 is saying by using equations, explain how internal energy, heat, work done are calculated for isothermal process. Let's go quickly to the answer. So we need to explain how the internal energy, heat, work done are calculated for isothermal process. So let's start on what is an isothermal process. Isothermal process is a process occurring at a constant temperature. When you have isothermal process, the process which is occurring at constant temperature. That means the change in the temperature of the system remains constant. So change the system in which the temperature remains constant. Here, when you have the temperature in isothermal process, the temperature, initial temperature, and the final temperature, they are the same. That means the change in the temperature is zero. So you have isothermal process, which is a process in which the temperature remains constant and the change in the temperature in that case is zero. In the thermal process, the heat can be added or it can be released just to keep the same temperature. When you have the expansion, remember expansion, you are decreasing the temperature, and for the temperature to remain constant, the system must absorb heat to make sure that the temperature stays constant. Again, when we are doing compression, compression increases the temperature. For you to keep the temperature staying constant, the heat should be released. Heat can be added or released to the system to keep the same temperature, to make sure that the temperature is staying constant. In the isothermal process, the temperature is constant and the change in the temperature is zero, because the final temperature and the initial temperature are the same, they are equal. That means the change in temperature is equal to the final temperature minus the initial temperature. The temperature are the same, then the dt or the change in temperature is zero for the thermal process. Here delta T, the change in temperature is zero for the thermal process. Again, the internal energy, I've seen that the internal energy is equal to NCV dt for any process. For isothermal process, the du internal energy is also equal to NCV dt. In this case, because the change in temperature is zero, that means for isothermal process, the internal energy is also equal to zero. Internal energy for isothermal process is equal to zero. Then, in this case, we have, remember, we have the internal energy is equal to Q plus W, or internal energy is equal to delta Q plus dW if you are in differential form. Then in isothermal process, the temperature stays constant. That means have the Q here plus the work done and the internal energy which is equal to zero. So that means the internal energy we have zero equal to Q plus W. Then we can say Q is equal to minus W, or delta Q is equal to minus W. The change in the heat is equal to minus the change in the work done, or the heat is equal to minus work done in isothermal process. So we're asked to determine how internal energy, heat, and work done are calculated for isothermal process. And here, when you want to calculate the heat, you should know that the heat is equal to minus work done, or the change in the heat, dQ is equal to minus delta W, and the internal energy is equal to 0. For isothermal process, internal energy is 0, the heat is equal to minus W, and delta Q is equal to negative W, if you want to write in differential form. So now, isothermal process can be either an expansion or a compression process. So we have the dQ is equal to negative dW, as we have seen. So the change in the heat is equal to the change in negative dW. So we might be having an expansion. When you're having it can be an expansion, the isothermal process, which is an expansion. In this case, delta T is equal to 0, and the internal energy is 0 for the isothermal process. dW is negative because you have an expansion. Remember, when you have an expansion, the work done is negative. During an expansion, the work done by the system is negative. The work is done by the system, and in this case, dW is negative. Now, to get this dW negative, because this one is equal to negative PdV, and you have an expansion, that means here delta Q has to be positive, so that the dW has to be negative. So we have dQ, which is positive. In this case, his heat is absorbed by the gas. To get the dW negative, this dQ has to be positive. So if dQ is positive, then the heat is absorbed by the gas. In expansion, to get a isothermal process, the heat must be absorbed by the gas to compensate the decrease in heat temperature. Because expansion, there is a decrease in temperature. Now, to keep the temperature constant, the heat must be absorbed by an isothermal expansion process. When you have the heat, the system absorbing the heat, in this case, we have what you call endothermic process, system which absorb the heat. And remember, here you have negative PdV. That means here negative. In this case, you have the positive. For an expansion, the dQ must be is positive. Expansion dQ is positive because you have the V2, which is higher than V1. Then the dW is equal to negative PdV. That means this term negative PdV will be negative times this negative. Then you get the positive. For isothermal expansion, the heat is positive. The heat is absorbed. The system is the endothermic process. Again, the thermal process can be a compression process. Process. During a compression, the temperature is increasing. We are reducing the volume. Of course, because we have in isothermal process, dT is equal to 0 and the du is equal to 0. Internal energy is equal to 0 because the change in temperature is equal to 0. The dW is positive because the work done is done by the system, by the surrounding on the system. If there is work done, compression, like the surrounding is doing the work on the system, and that work is stored as the internal energy. In this case, dW is positive. The work done here is positive. Remember, when you have a compression, the work done is positive, and when you have an expansion, the work done is negative. So then here the dQ will be negative. The system releasing heat. During compression, the dQ is negative. The system releases heat. Of course, Here, when you have the compression, the dW is equal to negative PdV. This dW is equal to negative PdV. But remember, the volume, the final volume is less than the initial volume. That means this P, this change in work done will be negative. This change in the work done here will be positive. Negative here and here, the change in work done will be negative because we have PDV, and the PDV here will be negative. In this case, then we have the dQ which is negative. Remember, for this term is equal to negative PDV. Negative PDV, and the change in the volume is also negative. That means this term becomes positive, but there is here this negative. That means the dQ will be negative. That means the system releases the heat, and you have an exothermal process. So when you have an expansion, because you have isothermal process, the dt is equal to 0, internal energy is also equal to 0, because internal energy is equal to NCV dt, and the dt is equal to 0. This internal energy is 0. The dW is negative, and for compression, dW is positive. The dQ is positive. Here, the heat is absorbed by the gas because we are having an expansion. And then, when you have an expansion, this dW is equal to negative PDV. This dW, we are not including this sign. Let's see this one. You have an expansion. That means when you have an expansion, it's equal to negative PDV. The work done is equal to negative PDV. At negative PDV, the volume is positive. That means we get that negative times this negative, we get a positive. That means dQ will be positive. It is absorbed by the gas. Contrary, when you have a compression, the dW is equal to negative PDV, but dV is also negative. That means negative PDV. dV is negative. There is another negative. Then, in this case, this term will become positive, but here we are still having the negative here. That means the dQ here will be negative. dQ is negative when you have a compression. The system releases the heat. In this case, we are in a exothermal process because the system is releasing the heat. Apart from this, isothermal process can be either reversible or irreversible. The thermal process can be a reversible, a process which is going slowly. This is the slow process. Here the pressure external is not constant. Remember, we have seen this where the difference between reversible and irreversible process. The pressure, external pressure, is approximately equal to the pressure of the gas. In this case, we can use the pressure of the gas in the formula. Remember, the dW, or the change in the work done, is equal to the negative integral the pressure of the gas times dV. Here we are using the pressure of the gas because the external pressure is approximately equal to the pressure of the gas when we are in reversible process. Then we can also have the irreversible process. During irreversible process, we have a fast process. The process is very fast, and here we have external pressure is always constant. Here we use the external pressure in calculating the work done, or the change in the work done in irreversible. We have the external pressure because the external pressure is always constant. Again, the external pressure is much different with the pressure of the gas. There is much difference with the pressure of the gas, contrary to the reversible process where the external pressure is approximately equal to the pressure of the gas. We have seen all these differences when we covered the reversible and the irreversible processes. So again, we have seen that the magnitude of work in reversible expansion is greater than the magnitude of work in irreversible expansion. Remember here, you can see that the magnitude of the heat is equal to the magnitude of the work done uh, during the isothermal process. That means also you can use this statement for the heat. You can say that the magnitude of heat absorbed in reversible isothermal expansion, because when you are in isothermal expansion, you have the heat which is the absorbed as you have seen. So the magnitude of heat absorbed in reversible isothermal expansion is greater than the magnitude of heat absorbed in irreversible isothermal expansion, because here the magnitude of Q is equal to the magnitude of work. If this scenario worked for the work done, also it works for the heat. So again, the magnitude of work in irreversible compression is greater than the magnitude of work in irreversible compression. We have also seen this scenario when we were discussing reversible and irreversible process. Have seen that the magnitude of work in irreversible compression is greater than the magnitude of work in reversible compression. So can say again, because in isothermal process, the magnitude of Q is equal to the magnitude of work. In this case, we can say that also the magnitude of heat released in irreversible isothermal compression is greater than the magnitude of heat released in reversible isothermal compression. Now, how do we calculate the work done in reversible isothermal process? When we are talking about reversible isothermal process, we are talking about expansion and compression. Reversible process which is occurring slowly. So here we are having the system where the temperature stays constant, and you have the system where here when you move to this way, you are decreasing the pressure, or you are increasing the volume. That means an expansion, and the compression is the reverse. You move from B to A. The volume may decrease and the pressure is increasing. How do we calculate the work? The work done. So here we calculate the work done as the area under the curve. The work done is the area under the curve. In this case, the work done is calculated as the negative integral of pressure of the gas times the change in volume. Because we have in reversible, here we use the pressure of the gas rather than using the external pressure. Let's see how do we calculate the area under the curve. In this case, we are integrating from A to B, So this is the point A and this is the point B. We are going to integrate. So you can replace this P. P is equal to nRT. P is equal to nRT over V. Then we can replace here the P by nRT over V. Then we can put aside the nRT is equal to minus nRT integral from A to B dV over V. So now what is the integration of dV over V? This is equal to ln V, but from A to B. So here minus nRT ln V, but the integration is VA to VB equal to negative nRT ln V. So this is the same as using V2 V1. This is the V2, the final volume, and the V1 the initial volume. And here dW equal to minus nRT ln V2 minus V1 is equal to negative nRT ln V2 over V1, because here negative is the same as dividing V2 dividing V1. So let's continue. So we have this reversible to negative nRT ln V2 over V1. Then we can change this ln to log by multiplying with 2.303. Then we get the work done reversible equal to negative 2.303 nRT log V2 over V1. So remember, we have discussed the Boyle's law at constant temperature. When you have the constant temperature, the pressure of a given quantity of gas vary inversely with its volume at constant temperature. That means the Boyle's law says PV is equal to constant at when you have constant temperature. That means P1 V1 is equal to P2 V2. then V2 over V1 will be equal to P1 over P2. Then here we have V2 over V1, which can be replaced by P1 over P2. In that case, we have the work done reverse equal to nRT ln P1 over P2, which is equal to negative 2.303 nRT log P1 over P2. So now how do you calculate the work done in irreversible isothermal process? In irreversible isothermal process, we are using the external pressure than using the pressure of the gas. External pressure V2 minus V1. And in this case, we are replacing the value of V2. So we can replace V. PV is equal to nRT. V is equal to nRT over P. Then here we can replace this one as nRT2 over P2. And here nRT1 over P1. Here D is equal to nRT2 over P2, nRT1 over P1. So you can put nR aside. You can put this nR aside. Then you get my negative nR P external T2 over P2 minus T1 over P1. Again, in the isothermal process, T1 is equal to T2 because we have isothermal expansion or compression. In this case, the final temperature is equal to the initial temperature because the temperature stays constant. Then we can say this T2 and T1 as a T because the T2 and T1 is the same. We can replace this T2 and T1 as a 1T. In this case, we get negative nRT. Keep this T aside, 1 over P2 negative 1 over P1. We are using this T because this T2 is equal to T1 is equal to T in when you have isothermal process, temperature is staying constant.